Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our third set of notes dealing with Chapter 17 and 18. Today we'll be getting in depth into reactions as we get into what are called reaction mechanisms. Now, most chemical reactions actually occur as a series of simpler reaction steps. So when we see a reaction, what we're typically looking at is what's known as a complex reaction. Collision theory says we have to have a collision to have a reaction. So when we have a reaction that looks like this, two NOs plus two H2s make N2 plus two H2Os, what this is really implying on the surface is that we have four particles simultaneously colliding with each other when this reaction occurs. And while it is likely that one particle might have enough energy to decompose, or two particles may collide with each other, anything beyond two things simultaneously colliding at the exact same instant in time is getting so mathematically improbable that it just can't explain the rapid reactions that exist in everyday life around us all of the time, because some reaction rates are incredibly fast. Well, four things simultaneously colliding just doesn't happen that often. So this is really not a look at on a particle level exactly how this reaction is occurring. This is an overall look at what we call a complex reaction. So this is actually not a simple series of reaction steps, but this is an overall complex reaction. So it's really just unlikely that four molecules are going to simultaneously collide. So that means that this can't be how this actually happens on a particle level. Well, how does it really happen on the particle level? That's what's called a reaction mechanism. It's a complete sequence of elementary steps, simple reactions that are actually looking at what's happening on a collision by collision basis that overall would make up a complex reaction. So let's say these three reactions, two NOs colliding, an N2O2 and an H2 colliding, an N2O and an H2 colliding. In every case, we have simple things, two things colliding. Those are very explainable reactions that could happen in a very fast way. So these, it's called the molecularity. Some things are unimolecular, which means one molecule doing something. Some are bimolecular, which means two molecules doing something. Anything past that and it just is too many things colliding to explain what we see happening in everyday life. So every one of these is what we call an elementary step, a simple reaction of two particles colliding. So these are elementary steps. But if I add them up and cancel, I get what's called the complex reaction or the overall reaction. So that's what I mean by reactions that we see balanced are often complex reactions or overall reactions. They're not really on a particle level how the reaction is occurring. That's what the mechanism's job is to look at it on a simple particle by particle level or basis. Could a reaction, how would a reaction actually occur? So if you look at this one, N2O2, there's N2O2s on both sides, so they're going to cancel. There's an N2O on both sides, they're going to cancel. And if we add up what's left, because nothing else cancels, you'll see we get two NOs on the left, we have two H2s on the left, we have an N2 on the right, and we have two H2Os on the right. So those three simple reactions would add up overall to the bottom reaction occurring. So these are our simple elementary steps that make up what's called our mechanism. And adding them all up and looking at overall what's going, this would be what's called our complex reaction. It's just the overall reaction if we add up and cancel everything. Now, why do we cancel? Well, because we're creating N2 here, and then we're using it there. So it wasn't there at the beginning. It's going to exist for a short time in the middle, and then it's going to get used up. So it's not going to be there at the end. So things that appear on both sides are going to cancel each other out, and they're going to make up what we call intermediates and catalysts, which are terms we've heard before, but we're going to look at more in depth. Now, before we get into intermediates and catalysts, I want you to understand something about a reaction mechanism. All of the different reactions are going to occur at different speeds. Somewhere in our reaction series, we're going to have a slowest reaction, and that's going to be called the rate determining step. So the slowest elementary step is our rate determining step. And you can think of this like a relay race. If we have four people involved in a relay race, three world-class athletes, and then myself, an almost 50-year-old chemistry teacher that's a little too heavy and a little too out of shape, if you look at our overall time, we have three world-class athletes and myself. Their times are going to be very fast compared to mine. So Who is going to have the biggest impact on our overall time? Well, it's going to be me because I'm going to be by far the slowest. And the same thing is true with reactions. So let's look at this proposed reaction sequence that we just looked at a second ago, how these three form a mechanism that would add up to the bottom reaction. Well, let's say the first one is fast, the second one is slow, and the third one is fast. Well, what that fundamentally means is this particular reaction here in the middle, the second step, is going to be our rate determining step. That's going to have the biggest impact on our overall time for this reaction to happen. If that first reaction is incredibly fast, we basically make N2O2 and then we wait for it to react with a hydrogen, and that's going to slow us down. So the first step really doesn't have a big impact on our time. It happens really rapidly. But waiting for the N2O2 to react with a hydrogen, that's going to bog us down. And as soon as we make N2O, it's going to react with other hydrogen there and rapidly make the other thing. So once again, that's not affecting our time that much. But that middle step, that's going to have a big impact on our overall time. And that's why we call it the rate determining step. Now, when you're looking at energy diagrams, there's always a way to determine what one is the rate determining step. We'll look at that in a second, but if we're looking at times, it's simply the slow one. And that the rate determining step is going to be the step that has the biggest impact on our overall rate. Now, I'd mentioned a second ago, if we actually look at the energy diagram for a reaction mechanism, not a simple elementary simplified step, one-step reaction, but if we actually look at all the steps that are occurring in a reaction, first off, the number of hills would represent each elementary step. So how many steps are in this reaction mechanism? Well, I see 1, 2, 3 hills. That means this is going to be a 3 elementary step reaction. So I'm going to have 3 individual reactions that make up our overall reaction. Now, what's the rate determining step? Well, remember, energy of activation is the front side of the hill. And this would be my energy of activation of the first reaction. This would be my energy of activation of the second reaction. And this would be my energy of activation of the third reaction. Between those three, the one with the highest energy of activation is going to be the reaction that's hardest to occur at any given temperature. And that means it's going to be the slowest. So in this particular case, our reaction mechanism, our largest hill, remember it's the front side of the hill, not the back side of the hill. Our largest hill would be the second step. And therefore that would be our rate determining step. And then overall, is this reaction endo or exo? Well, I could count up individual energy of individual steps, but that's really hard. It's a whole lot easier to just say, I started here, I ended up here, I lost energy. Overall, this reaction is therefore exothermic. So ignore all the stuff in the middle and just look at the beginning and the end. I started at a higher energy than I ended up with. I had to lose energy. That's exothermic. So that's an energy diagram of a reaction mechanism. When we looked at an energy diagram before, what we were looking at is the simplified overall energy of the reaction. And here we're looking at the energy of each individual step. Now, I mentioned we're going to look at mechanisms to understand better these things called intermediates and something called a catalyst, which you already are familiar with. Well, an intermediate is what we're going to tackle first here. An intermediate is a substance that's produced in one elementary step and then later consumed. Now, that later part is really, really important because if you look at something that cancels out, not there at the beginning, not there at the end, cancels out. An intermediate would be an example of that. It only exists in the middle of the reaction. Well, how do we know if something that cancels is an intermediate or a catalyst? Well, if it first appears as a product in our reaction sequence, therefore it's an intermediate. So we go back to this one. N2O2 was something that canceled out, and N2O was something that canceled out. And both of these first appeared on the product side and then later became a reactant. In other words, it was formed and then used. And that's exactly what an intermediate is. It's not there at the beginning. It's only there at the end. Or I should say, and it's not there at the end. It only exists in the middle. It's an intermediate. So N2O2 and N2O in this particular reaction mechanism would be examples of intermediates. They're things that only exist in the middle. And if you back up a second and look at our energy diagram, our intermediates are things that appear right here. There are products in our in-between steps. So when a reaction occurs and it makes something that then gets used, we've got an intermediate. So that's where our intermediates would appear in the energy diagram. Now, a catalyst is something a little bit different. That's like an intermediate, and then it's disappearing. I should say it cancels out when we look at our mechanism, but it's canceling out for a very different reason. A catalyst is a substance that appears first as a reactant in one step and then later is produced. So it's getting consumed at the beginning and then later it's getting remade again. So it looks like it's there at the beginning, it looks like it's there at the end, it looks like it did nothing. So a catalyst is something that we cancel out. Once again, there on both sides, it looks like it does nothing, but it first is appearing as a reactant. So when we look at this bottom reaction, this is the reaction for hydrogen peroxide. So hydrogen peroxide undergoes this bottom reaction right here. That's its overall reaction. It's a relatively slow reaction. So what can we do to speed it up? Well, it turns out that I minus mixed with hydrogen peroxide rapidly causes the decomposition. So I minus must be speeding up the reaction. And it's not being consumed. It's there at the beginning, it's there in the end in the exact same concentration. So it looks like it's there and it's not consumed, hence the catalyst. Well, why is it a catalyst? Well, in the proposed mechanism here for what happens when we add I minus, you can see that in this particular case, I minus is first a reactant and then a product. It's used and then made again. So it's there at the start, there at the end, looks like it does nothing. We cancel it out. But it first appears as a reactant. So by definition, I minus would be a catalyst. Now, how does that compare to an intermediate? We'll look at IO minus. IO minus is produced in step 1 and then used in step 2. So it's also going to cancel out. But it's first appearing as a product. And that means it's going to be an intermediate. So in this proposed mechanism for the decomposition of hydrogen peroxide, you can see we have a catalyst and we have an intermediate. And that ends our next set of notes over the chapters.